Hello, everyone, and thank you so much for giving me the opportunity to present my recent work at this year's conference on topics in astroparticle and underground physics. My name is Stefan Schulte, and I'm glad to introduce you to my latest project, which deals with dark matter as a pseudo Nambu-Goldstone boson and its interactions with top quarks. So this work was done in collaboration with Uli Heisch and Giacomo Policello. And for further information, you can find our preprint on the archive. Now, let me start by giving you a brief introduction. So I assume that everyone here is familiar with weakly interacting massive particles, or WIMPs, as the leading candidate for dark matter over the past decades. Now, the most popular WIMP models, like, for instance, the neutralino that you get in supersymmetric theories, are more and more challenged by the null results reported from the LHC and direct detection experiments in particular. And this motivates other models that avoid these constraints due to the structure of the interactions of the dark matter candidate with the standard model particles. Now, I'm going to talk about models in which dark matter arises as pseudo Nambu-Goldstone boson, or pNGB for short, from some larger symmetry structure at high energies. And depending on the exact realization in the UV, you can also describe the standard model Higgs boson as a pNGB, in which case it would be naturally light and the standard model hierarchy problem would be solved. So in such a scenario, you would have a viable dark matter candidate and solve the hierarchy problem, which is exactly what people wanted to explain with the lightest supersymmetric particle as dark matter candidate as well. Now, we are not interested in exact model realizations in the UV, but instead we study a set of generic operators that are relevant in these kind of models. And we distinguish two different kinds of interactions. First, operators which couple dark matter to the standard model Higgs via derivatives or directly, namely what we call the derivative and the marginal Higgs portals. And second, we have interactions of the dark matter with standard model fermions, where we have the Yukawa type and the current type interaction. Those either scale with the standard model Yukawa couplings or couple via derivatives as well. The F in front of the dimension 6 operators denotes the common decay constant of the pNGBs. Since the interaction of dark matter with the light standard model fermions is either Yukawa suppressed or momentum suppressed, one would expect these models to be less constrained by dark matter direct detection. But on the other hand, the scaling with the Yukawa coupling suggests an investigation of the interactions of dark matter with top quarks. And this is exactly what I want to talk about in this presentation. So let's consider some phenomenologically interesting processes. Now, at the LHC, you could imagine to produce such a dark matter candidate in association with top quarks. For instance, you can have two gluons in the initial state producing a pair of top quarks and an intermediate particle producing a pair of dark matter as depicted here in the left diagram. Similarly, you could produce dark matter along a top quark and a W boson if you start with a bottom quark in the initial state. Now, the top quark usually decays into a bottom and another W boson, and the W in turn decays hadronically or leptonically. So we constructed three orthogonal signal regions. For the production of dark matter along pairs of top quarks, we have signal region 1 targeting events with one single highly energetic charged lepton, and signal region 2 searching for two leptons. Our third signal region targets the TW final state and also searches for the fully leptonic decays of the Ws. The analysis details of our work are described in our preprint, but similar signatures have previously been studied in the light of dark matter simplified models by the Atlas and CMS collaborations in a very similar way. We implemented 4 of these into Checkmate, which we used as a validation of our approach and as a reference. Now, regarding our Monte Carlo setup, the generation and showering of signal events was done in MudGraph and Pythia at leading order, for which we assumed a 5% systematic uncertainty. And for the backgrounds, that is TT bar production, TW, and all kinds of combinations of electroweak bosons plus jets, for that, we mostly relied on PowHack with next to leading order accuracy assuming a 15% systematic uncertainty. Now, you can probe this Lagrangian that I've shown you before also in other channels. For instance, there already exists a study on the derivative Higgs portal and how this can be constrained by off-shell production of the Higgs and the vector boson fusion channel, which I will come back to at a later point. Now, we also had a look at the monojet channel, which is interesting regarding, for instance, this diagram here on the right. But we found that the constraints you get there are not as strong as the ones from this Tx plus missing energy channel. Another constraint that we get from precision physics at the LHC would be invisible Higgs decays. Now, the dark matter Higgs operators obviously lead to tree-level contributions to the invisible Higgs decay with whenever the dark matter is light enough, such that this decay is kinematically allowed. But at the loop level, invisible Higgs decays could also potentially probe the dark matter fermion interactions, which can be explained by the diagram here in the middle, for instance, for the current type interaction, and on the right for the Yukawa type interaction. And when you do the calculation, it turns out that the sum of all diagrams of the type here in the middle actually vanishes. So invisible Higgs decays can only probe the Yukawa type interaction of dark matter with standard model fermions, but not the current type interactions. Now, in general, we just computed the partial decay width of the standard model Higgs boson and compare the implied Higgs to invisible branching fraction to the projected high Lumi LHC limit. This gives us quite strong constraints, as I will show you later on. Now, regarding direct detection, you can couple the pNGB dark matter to the U1 hypercharged gauge boson of the standard model, which then induces electromagnetic scatterings with atomic nuclei. Or via quark loops, you can couple the dark matter with SU3 field strengths, and such that the dark matter can interact with the gluons inside nuclei. Both these diagrams that you can see here turn out to give very strong exclusion bounds from direct detection. And with the Lagrangian that is displayed here, you can then compute the spin-independent dark matter nucleon cross-section that you can see here. Now, the exact formula is not so important right now, but you can take this expression and compare it to the current 90% confidence limit published by the Xenon collaboration. And this then results, again, in very strong constraints on all of the model parameters, except for the derivative Higgs portal. Now, of course, in the end, we are interested in explaining the observed relic abundance of dark matter in the universe. And for this, and also for indirect detection constraints, we computed all the relevant S and P wave contributions of the different annihilation channels. And the dominating annihilation channels always depend crucially on the dark matter mass. For indirect detection, we also considered the annihilation of dark matter pairs into pairs of monochromatic photons, which can be achieved via TAUP or W loops. And in general, you get very strong constraints whenever the dark matter mass is around half of the Higgs mass, leading to resonant on-shell Higgs exchange. In the end, for our numerical analysis of both the relic density and indirect detection constraints, we relied on the Micromegas code provided by colleagues from the Technical University of Munich, for which we are very grateful. And our analytical calculations basically serve as a cross-check that we understand the output of Micromegas. Now, let's have a look at some results. So here on the left, we have only considered the derivative Higgs portal operator to be non-zero. And you see an exclusion plot with the dark matter mass on the x-axis and the common pNGB decay constant on the y-axis. We see that if kinematically allowed, a large region of the parameter space is ruled out due to invisible Higgs decays for small dark matter masses, which is this light green domain. And the gray band located around half of the Higgs mass is the constraint from indirect detection, that is gamma ray spectra from dwarf spheroidal galaxies. Now, for larger dark matter masses, we see the only way to probe pNGB dark matter are collider searches, which you can see here at the bottom right. Here we observe that the constraints we find for Tx plus missing energy, shown in this dark bluish color, are not as strong as the ones that you get from the VBF channel, here displayed in orange. However, I should mention that the VBF analysis assumes systematic uncertainties of 1% at the high Lumi LHC, whereas our analysis is a bit more conservative since we assume 15% background uncertainty. All shown collider constraints are high Lumi LHC projections, so they assume 14 TeV as center of mass energy and an integrated luminosity of 3 inverse autobahn. In general, we can say that collider constraints are by far not strong enough to exclude models which also explain the dark matter relic abundance, which is realized along this dark green line. Direct detection experiments are not sensitive to the derivative Higgs portal operator as mentioned before. However, if we add, for instance, the Yukawa type interaction with fermions, this changes. All the other bounds remain somewhat similar, but the direct detection constraint now dominates the collider constraints up to the TeV mass scale. Still, the sensitivity is not strong enough to test whether pNGB dark matter explains the relic abundance. And now also the Tx plus missing energy constraint is stronger than the VBF constraint, which is due to the fact that VBF is not sensitive to the dark matter fermion couplings. Now let's add on the left plot the current type interactions, and there you see a very similar picture as on the right with the Yukawa type interaction. But I want to point out the shift of the relic density constraint for small dark matter masses, which is due to dark matter annihilation being dominated by p-wave annihilation into pairs of bottom quarks, which is only relevant for non-vanishing current type interactions. Now, this brings me to my conclusion. So collider searches are essential for a complementary search strategy for pNGB dark matter, and the Tx plus missing energy channel gives competitive constraints compared to the VBF Higgs production channel. We have further found that you get very strong limits from dark matter direct detection experiments if you include loop-induced processes with the dark matter fermion interactions. So all in all, according to our analysis, pNGB dark matter still remains an interesting candidate to explain the dark matter puzzle in the universe and solve the hierarchy problem. And for more information, you can have a look at our preprint. And with that, I would like to thank you all for your attention.